This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, so let's get started. So, in the past one or two lectures, we learned about this complex potential. Right, and just a recap, why are we actually using this complex potential? Why do we want to learn this? Right, and it actually simplifies things quite a bit. Right, and it's also very easy to show that this complex potential satisfies both our continuity and momentum equations. Okay? And finally, we can apply conformal transformations very, very easily, which again ties back to what I mentioned in the first week of lectures, where we want to try and predict the flow over an airfoil, right? And using conformal transformations, which you will learn next week or the week after, right? We can then convert our flow over a cylinder to a flow over an airfoil using conformal transformations. Right. So in the previous lecture, then we looked at the flow over a cylinder examples and try to express things in terms of the complex potential. But you guys can review that lecture yourselves, right? And we should also know how to express all our other simple flows in terms of complex potential. Okay? Now, when we have our complex potential function, which is W equals to phi plus I psi, we can very easily find our velocities u and v, right, in Cartesian coordinates, which is the equation on the left here, and in cylindrical polar coordinates on the right-hand side here, right, where the exponent I theta dw dz is going to give you ur minus I u theta. Okay? And you all should know that z is a complex number, x plus I, y, and I can express that as a complex exponent, r exponent I theta. And using Euler's formula, you should know that exponent I theta is just equals to cos theta plus I sine theta, right? So this term here is just basically that from Euler's formula. Okay, so I guess most of you have been to this week's tutorials, yes? Right. So if you've been to this week's tutorials, you've probably seen this new simple flow, which we have introduced in the tutorials, but not in the lectures yet. But I'll be introducing it to you today, which is the potential vortex. Okay, but hopefully most of you have seen this in your previous fluids course. Right. So an irrotational vortex is defined as having no radial velocity, okay, and the azimuthal velocity is equal to a constant divided by r, which is some function of the radius, okay, or the radial distance from the potential vortex. Okay, and this gives you circular streamlines, right? So the streamlines of a potential vortex are circular. Okay. Now, if I consider an element on one of these streamlines, okay, I can then calculate and see what the vorticity is on one of the streamlines, right? So this is the equation for vorticity in cylindrical polar coordinates. So remember, I know ur is equal to 0, so my last term just cancels out. And u theta is just defined as a constant divided by r. Therefore, if I differentiate this, partial differentiate this with respect to r, I'm going to get negative c over r squared. Okay, so I'm just going to substitute my terms back into the equation for vorticity. Okay, and hopefully you can see that there is zero vorticity, right, for this potential vortex. Okay, so when we define our vortex as such, it is an irrotational potential vortex. Okay. However, when you have a solid body, right, typically when you have a solid body, and if it follows a streamline, right, what is going to happen is that your solid body is actually going to follow the streamline, right? It's going to translate, and it's also going to rotate, right? In this case, it's going to rotate in the in the anti-clockwise direction. Okay, and I'll show you an example of a solid body rotation. Let's see. How do I do this? Oops. Right, so I have a solid body here. Okay, and this is the streamline. Right, and you can see for a solid body rotation, this fluid element is not only translating, but it's also rotating, right? Okay, and as it goes around this streamline, it would have made exactly one rotation. Right, it has rotated one revolution, right? So this is a solid body rotation. Okay, but if you look at how we have defined our potential vortex, right, where u theta equals to c divided by r, right, you can see that my velocity, my azimuthal velocity is going to be higher as r is smaller, right? So my velocity here is actually larger than the velocity here. Okay, and this will cause a clockwise rotation. Right? So for a potential vortex, what actually happens is you have you have your fluid element just translating, right? If you look at this red thing here, it's just translating, right? And the blue is your solid body rotation. Okay. So in a potential vortex, your fluid element is just translating. It doesn't rotate because the flow is irrotational, right? Right, so it is irrotational-ish because there is one point where vorticity is not zero. Can anybody guess? Where? So it's irrotational all over here, but there's one place at the center, all right? So only at the center it is not irrotational. Okay, there is rotation only at the center. Okay. All right. Now I'm going to introduce to you this term called circulation. Right, and circulation or gamma is defined as the line integral of velocity around a closed loop. Okay, so consider this flow here where we have streamlines. And I'm just going to have some arbitrary line, closed line. Okay, and I can calculate the circulation of this closed loop here, right, of this shape. So if I consider some small element along this line here, ds, right, and I know that I have this streamline which has some velocity v at some angle to ds. My velocity tangential to the surface ds is just going to be v times sine alpha, right? Okay. So this term here would be my velocity parallel or tangential to my line, in this case ds, right? And I just integrate it over this whole, this entire line here, this closed loop, right? Okay, so if I do that, I'll get circulation. Okay, so let's try and calculate the circulation along a streamline, along a circular streamline for our potential vortex. Okay, so if you look at our streamlines, our circular streamlines, the velocity u theta is always tangential to our streamline, right? Okay, so therefore, I can replace v sine alpha with just u theta, right? It's always tangential. Okay, and I then just have to integrate it for this circle, which will give me u theta to pi r, right? So I get my circulation is u theta to pi r, and therefore I can rearrange it to find my azimuthal velocity as a function of circulation and radial distance. Okay. Now, I can compare this with the original definition of a potential vortex, which is u theta equals to c, some constant divided by r, right? And I can then show that that constant c is just equals to my circulation divided by 2 pi. Okay. Right, and circulation taken about all streamlines on a potential vortex is the same. Okay, so hopefully you can see that it does not matter if I take my circulation along this streamline or along this streamline. My circulation is going to be constant for all of those cases. Okay. Any questions so far? Everything okay? Yep. Right. So circulation is also very closely related to vorticity. Okay. It's basically the surface integral of vorticity. Okay. So circulation is equal to surface integral of vorticity. So we also know that there's only one point in a potential vortex where there is vorticity, okay, and that is at the center of the potential vortex. So that's why a potential vortex is also known as a point vortex. Okay, everywhere else is irrotational, has zero vorticity, except here at the center there. Right. So if let's say I consider this area here, okay, the area under this black circle, my circulation is just going to be equal to 2 pi c. Right? Everyone agree with me? Yep. Okay, and can anybody guess what's my circulation going to be for this area here? Gamma is going to be equal to? Is it going to be the same? (50-50), yes or no? 50-50 chance. Yes. No. Yes, it's going to be the same. All right, it is going to be the same. Okay, it's still going to be 2 pi c. Right, your circulation is still going to be equal to 2 pi c. How about here? Is circulation going to be, okay, circulation now is going to be 0, all right? Because you know that everywhere else is 0 except at this singularity here. So circulation is going to be equal to 0 for this case. Okay? All right. So, right, let's find our stream function and potential function for a point vortex. Okay, let's try and do this together. Okay, so I've written down here u theta and ur for a potential vortex. Now, I hope it should be quite familiar, right? Hopefully you can make this relationship on how your potential vortex is quite different to a source and a sink. Okay, if you notice that for a potential vortex you have 0 radial velocity, okay, but in a source and sink you have 0 azimuthal velocity. Okay, and for potential vortex, your azimuthal velocity is just gamma divided by 2 pi r. And for a source and sink, your radial velocity is just q divided by 2 pi r. Okay, so hopefully you can see, I guess, some similarities and differences between a source and a potential vortex. Right, so we want to find our stream function, potential function, and later on our complex potential. So let's find our stream function first. So we know that ur is just going to be equal to 1 over r del psi del theta. Okay, you should know this at the back of your head. Right, and u theta is just negative del psi del r. Okay, it should be fairly straightforward. You know that you got 0 radial velocity, right? So therefore del psi del theta is just equals to 0. Okay, and for this equation here, you know that del psi over del r is just going to be equal to negative gamma over 2 pi r. Okay, and I'm just going to call this 1. Right, so I'm going to integrate both my equations on the left and right. Oops. Okay, so on the left hand side here, I'm going to get some function f1, some function of r, f1, right? And on the right hand side here, I'm going to get negative gamma over 2 pi ln r plus some function with respect to theta. Okay, and we know that for the equations to be compatible, we therefore know that f1 R is going to be negative gamma over 2 pi ln R, okay, and F2 theta is just equals to 0, okay, and the constant that we have is just 0. So therefore, stream function for a potential vortex is just negative gamma 2 pi ln R. Okay, all good? Or am I going a bit fast? Yep. Right, so now I have the stream function. I want to find my potential function. Okay, and I'm going to just use the relationship between stream function and potential function in polar coordinates. Okay? So, we should know that it's a bit small. Right, so we also know, what do we know? I don't know what we know. Anyway, so we need to know the relationship between psi and phi. Yes, that's what we need to know. So del psi over del r equals to 1 over r del phi del theta. Okay, we need to know this. Okay, and I'm just going to substitute 1 into this relationship which we have there. Right, and if I substitute, I'm going to get, If I substitute equation 1 into 2, I'm going to get del phi over del theta equals to gamma over 2 pi. Right? Everyone agree? Okay, and the easy part is then just integrating it so that I find phi. So phi is therefore just going to be equal to gamma theta over 2 pi. Oops. Okay, any questions before I move on? Good. All right, so we have our stream function, our potential function, right? And then finally I can just put them together to get my complex potential. Okay, so therefore the complex potential. Okay, so complex potential is just W equals to phi plus I psi, which is just gamma theta divided by 2 pi plus I negative gamma over 2 pi ln R. Okay, now I want to take out my gamma over 2 pi. Sorry, what do I want to take out? Yep, I want to take out gamma. Oops, don't delete. I want to take out gamma over 2 pi from this equation here. Actually, I'm going to take out negative I gamma over 2 pi. Right. So I'm going to end up with I theta, okay, and plus ln of R. Okay, so I've just factorized the equation. Now, there is a trick here. Okay. There's a bit of a trick here. I want to combine these two terms together. Sorry? Okay. So I want, the trick is I want to combine these two terms. I have to write this in terms of ln, right? Because ln plus ln, I can then make it into a ln multiple, right? So I want to make this into a ln. So what am I going to get? Ln E I theta, right? Okay, so that's a bit of a trick which you have to do. Plus ln R. Okay, and if I do that, then I can then very easily combine my ln terms. So it's ln R E I theta. Okay, and what is R E I theta? Z. Very good. Okay, so it's just Z. So I end up with negative I gamma over 2 pi ln Z. Right, so this is the complex potential for a point vortex or for a potential vortex. Okay? So you should be able to derive the complex potential for other simple flows as well. For a source, a sink, uniform flow, doublet, right, and so on and so forth. Okay, so we're going to do one more extra step. We want to find velocities. Right, and now we have the complex potential. It's quite easy to find our velocities. So let's find our velocity u and v. Okay, and to find velocities, I just have to differentiate w, right, with respect to z. So dw dz is going to give me negative I gamma over 2 pi z. Okay, and I'm just going to rewrite z as x plus iy. Oops, 2 pi x plus iy. And hopefully you remember that that's just going to give me my velocity u minus iv. Right? So I'm going to split up my imaginary and real terms. So I'm going to multiply it with the conjugate, complex conjugate, x minus iy to the top and bottom of this term here. Okay, so I'm going to get negative I gamma over 2 pi x plus iy, x minus iy over x minus iy. Right, and I should get gamma divided by 2 pi x squared plus y squared minus y minus ix. Okay, and it's minus y here because there's minus I times minus I, which is I squared, and I squared is minus 1. Okay, to get this. Right, and very easily, all I have to do then is to show that therefore u is just the real of dw dz. Okay, and therefore it's just negative gamma y over 2 pi x squared plus y squared. And v is just the negative imaginary of dw dz. So that's just gamma x over 2 pi x squared plus y squared. Right, any questions? Clear? Crystal clear? Or clear as mud? Right, it should be, if you're a bit confused, I think the tutorials will I guess help you out a little bit. Okay, so please do the tutorial questions. I know the tutorials are a bit short and you can't cover all the materials during the tutorials, so please try and do the rest on yourself at home. Okay, there's only so much time that we can help you in the tutorials. Right, but this is basically how you find your velocities, right, for a complex, for a potential function, for a potential vortex. Sorry. Okay. Okay, so in MATLAB, you can very easily then plot the velocities u and v. Okay, and I'm going to use Quiver to look at the velocity vectors for a potential vortex. Okay, so your velocity vectors will look something like this for a potential vortex. Okay, and please remember that as a source and a sink, similar to a source and a sink, a potential vortex has a singularity when r is equals to 0, right, at the center. Okay, so you will have to do error trapping at the center. Okay, if not, your velocities will blow up to infinity. Now, here's a single lonely potential vortex. Okay, and this potential vortex cannot induce any motion, right, because it's a load. So it remains stationary. But now if I have a pair of vortices, we can induce motion to each other, right? So if I look at this potential vortex on the left, all right, it's rotating clockwise, and it's going to induce some motion downwards to the potential vortex on the right, right? And the potential vortex on the right-hand side, which is anti-clockwise, is going to push this potential vortex on the left downwards. Agree? Yep. So what's going to be the net effect of this movement? Assuming that both of them have equal strength. Circulation. One is pushing it down, the other one is pushing it down, so it's both going to move down, right? So both of these potential vortex will move downwards, right? And a few cool videos to show. Oops. Right, so we have smoke, blue and red smoke on the left and right, and an aeroplane is going to go past this smoke. Right, and you can see that you have two vortices, tip vortices forming at the edge of the airplane. Whoops, a bit too fast. Right, but hopefully you can see that the one on the left here is rotating clockwise, right, and the one on the right is rotating anti-clockwise, and they're mutually inducing each other to move downwards. Okay? Right, we also observe these tip vortices forming at the rear spoiler of an F1 car, right? But hopefully you can see that the direction of these vortices are a bit are in the opposite direction, right? You can see that the vortices on the right is rotating clockwise, and on the left is actually anti-clockwise. Right, I just scrub to a. Okay, and this is because your rear spoiler is used to create downforce, right? It's opposite to an aircraft where it's supposed to create lift. And that's why you have these vortices forming at the tip, which is in the opposite direction of the airplane. Right. Thought I'd show you another video. Who doesn't like videos? Right. So we have this aircraft which has flown past, right, and we have some station located on the ground where it's feeding out smoke to trace the flow. Okay, and after some time, after the aeroplane has left, suddenly we see these large vertical structures occurring. Right, and if you don't have this smoke, you are not able to see these vertical structures, right? Okay, and it's quite interesting because the plane has moved away, quite far away, right? But only now, after a few minutes, I think you only see these structures occurring. I'll show you again. Right, and this is really quite important, especially if you are in a runway, right? You want to make sure that you have a safe minimum amount of time before a plane takes off or departs, right? Because this kind of large swirling motion would affect a plane taking off or landing, right? So, yeah, so these are two pair vortices, all right, and these cases have both these vortices have opposite signs, all right? So I just showed you that these two vortices will move downwards. Okay, one thing to think about when you go back home before you sleep is, what happens if, let's say, I have a wall here? If I have a wall here, how are my vortices going to move? These two vortices going to move, all right? Something to think about before you sleep tonight. All right, another case is when you have two vortices which have the same signal, same sign, right? So both are rotating clockwise, and hopefully you can see that these vortices will just rotate around each other, okay? So just rotate. Okay, and the red line which you can see here is just the path line of the vortices. Okay, now when you have three vortices, okay, it's going to get a bit complicated, right? And it's not so easy to predict, I guess, by hand, but you can use MATLAB to predict the flow quite easily. Right, so I have one vortices on the top left here, which is rotating clockwise, which would induce a downward motion, right, to the vortices, to the vortex on the right, and at some diagonal velocity to the vortex, this vortex here. All right, and this other vortex here, which is rotating clockwise as well, would induce motion to the other two vortices. Okay, and finally, the third vortex, which is rotating anti-clockwise, would also induce some motion to the other two vortices, point vortex, right? So the movement would then be the sum of all these different effects, all right? It will be the sum of all the effects of the point vortices, okay? So you can see that it can become quite chaotic. Right. Okay, so before I end, I thought I'd show you something quite interesting about point vortices. So I'm going to have don't crash. Oh, what's going on? Okay, MATLAB crashed. Give me a minute. Oh, gosh. Right. Okay. Right, so this is a map. Okay, I think this is Ireland here, and this is the UK. Right, you have Iceland here, and this is the country that the President of the United States wants to buy. Greenland. All right. So we're going to just model cyclones using potential vortex, right? So we have two cyclones, right, modeled by a potential vortex in Greenland, right, and one just off the shore of Ireland and UK, right? And at the same time, we have a volcano erupting in Iceland. Okay, and we want to predict whether the ashes from this volcano is going to hit the UK, right? And we can kind of use potential vortices to model this flow, right? Very crudely, but I mean, it's quite fun, I guess. So, right, so, shucks. Right, so these are your smoke particles, ash particles, and your point vortices, which are your tornado is moving. And you can see that, right, the UK gets hit with all this ash particles from Iceland. Right, so I guess that's just, one way of using point vortices to model some complex, relatively complex flows, right, which are time varying as well. Okay, so that's all for today's lecture, right? And on Monday, we will continue with looking at a flow with a doublet and a potential vortex. Thanks.
Yeah, sure. Can you explain again the singularity?
Yeah.
It's on the sink and the tablet.
Yes, so a doublet has it, a sink has it, a source has it. So
for example, this is tablet. How can I?
Okay.
Is it in the origin?
So if you go back here, well, I guess you can see it here. So you see your stream function goes to infinity, right, when r equals to 0. So that's just a single, so it gives you incorrect values. It's just an infinite value.
Yeah.
So that's a single direction.
So the streamline, should it go through the origin or not?
So that's why at very close to origin, your velocities are very, very large. Very, very large. So when you're doing the assignment, right, you want to make sure that when your particles are very close to the origin, you want to set the velocity to 0. Or else the velocity will be close to infinity, and then you get very weird looking stream path lines of your particles.
Yes. Thank you.
Okay, no problem.
So in the last lecture, we reached this particular point, and then we multiplied it by the conjugate,
Yes.
and so we have this whole denominator.
Yes.
So by the formula a plus b and a minus b, we actually get x square plus y square, the whole square. And the slide it was minus.
Oh, is it? What? No. Yeah, I think this is correct, right?
Yeah.
So x squared minus y squared, right?
Yeah.
So that would be
so the whole
everything
term
will be
is a. This is b.
Yep.
And this is a. So this is a plus b, a minus b. So a plus b, a minus b is a square minus b square.
Yep.
Which is x square minus y square
But
minus of this particular thing squared. So if you solve this, you get this I've left over here. So 2 square is 4, x square y square, I square is minus 1, and minus 1 minus is plus.
really?
Yeah.
Wait, let me have a look. What? It hang again. What? Sorry, so this is what?
Last lecture.
Last lecture, yeah? Okay, so check the time. Last lecture 11. Okay, so trip back. So which one? Is it this one?
Yeah. So you've written x square minus y square the whole square. It should be plus, I guess, because when you solve it,
Really?
yes. We just need to solve the complex conjugate as a plus b, a minus b.
Hold on a second. Really? Does it?
Yes.
Oh, I forgot a square there.
Yeah, so square is there, but the center has to be plus.
Okay, so minus. So this will be 2 minus, right? 2. Oh, shucks. Yeah, it has to be plus, huh?
Yeah, that's what.
Okay, I'll double check again.
Yeah.
Okay, I'll double check.
And so one more doubt I had. Will there be any tests regarding MATLAB? Regarding any tests?
No, it shouldn't be any.
No. Okay, so if you could just check it out, because I've done the entire calculation, it leads to x square plus y square. It's like easy. Okay.
Yep, I'll just double check.
Yeah.
Thanks for letting me know.
Hey, I just want to ask about the more intuitive meaning of extension.
Yep.
Yeah, sorry, explanation. I'm still like wondering like how does it work or what's it mean? Like I'm trying to like wiki it, but we have like some sort of surface,
Yep.
and then you have like streamlines, and you have like your velocities and the streamline, and you're finding like some sort of line integral of velocity
Yes, that's right.
against that surface,
Yep.
right? And then so what does this come to? Like what is this for? Like what do you think? Like is this what are we trying to do? I don't really understand that.
Yeah, I guess it's
Weird for me.
how about if you think about it as the surface integral of vorticity?
Surface integral of vorticity.
Yeah, maybe that would be a bit easier. So, you know, vorticity makes the flow, I guess.
The rotation of vorticity.
Yep, right. So if you have an area, right?
Yeah, sharp.
An area.
Yeah.
Okay, and you take the surface area, area integral of vorticity, that is also equals to circulation. Right. So
Yeah.
I guess
Definition.
yeah. So basically, let's say you have a surface, and that area under that surface has zero vorticity,
So it won't spin. Yeah.
so it won't fit. Yeah. So basically, circulation in that surface is zero. Zero. Yeah. Does that?
I'm sort of hearing like these definitions, and I'm like, yeah, those are the definitions. I'm getting like this intuitive sense of
Yeah, I get.
feeling it.
Yeah, I guess in potential flow, everything is zero except at certain points, like
Yeah,
the potential
yeah,
context. But
yeah.
maybe if you want to, I guess you want to quantify, right? How how vigorous the flow is moving or is being
Yeah.
is rotating, right? So circulation will give you an indication of
If that flow is sort of rotating.
yes. Yeah. I'm not sure whether that's a very good explanation, but that's how I.
You understand?
Yeah.
I think I have to like think about it for a while.
Yeah.
Yeah.
It's. I probably rushed through it a little bit as well just now. But, yeah.
Okay, I'll have more look into it.
Okay.
I'll ask more questions later.
Sure. Okay.
I'm not sure how this images could show a rotation.
Oh, okay. So it's irrotational because if you see this now, my fluid element is just translating. Only at the center is rotating, right?
Yeah, but as you said, the velocity and the different size is different, so it will rotate.
No, so it balances out the solid body rotation, right? So normally a solid body rotation would rotate with the pendulum, right? But the potential vortex is irrotational because the velocity here is higher than there. So instead of it translating and rotating, because your velocity here is higher than there, it just translates.
So it is called rotational? No.
No, so that's rotating, right? So that's rotating.
Yeah, and this is called irrotational.
Yes. So in potential, in this point vortex, it is doing that. It's not, but normally, right? It would.
Yeah.
In normal situations, it would move that way, right? Yeah, it would translate and rotate. But in these cases, it's just translating, zero rotation. Yeah. And it only rotates at the center.
So in the potential vortex, the velocity is still different. These two sides.
Yeah, because of this, right? U theta equals to C over R. So R is smaller here, so U theta is higher. So that's why it's instead of moving this way, it's just moving this way.